Hi, this is Dr. Dearden, and I'm doing a review for Unit 1 of Physical Science 100. Now, the way this review is going to work is I have a lot of information on this very first slide. It's sort of an outline of what I think is most important from Unit 1. And so I'll try to cover a lot on this first slide, and then there are quite a few practice questions, clicker type questions. And what I suggest you do is, as you see each of those questions, you pause your video, attempt to answer the question, and then I'll go ahead and explain what's going on. There's also some more review material in there as we'll go along. That's probably everything I need to say to start with. So in Unit 1, we started off talking about the laws of motion and the laws of force. And in particular, when we're talking about motion, which I'm going to focus on, we talked about force laws too, but I'll focus on motion right now. We noticed that there were three laws that Isaac Newton put forward many years ago that can be used to explain motion. So Newton's first law is the law that describes what happens when there are no forces. When there are no forces, you have uniform motion. And uniform motion, you'll recall, is defined as motion at constant speed and direction. So if either speed or direction or both is changing, then your motion is not uniform, it's accelerated. The second law deals with what happens when you have a force present, and that's what causes accelerated motion. So if you have an accelerated motion, that implies that there is a force present that is an unbalanced force. The net force is not zero if you have accelerated motion. So remember that acceleration is a change in speed and or direction. The other way I like to do the second law is just in terms of the equation force equals mass times acceleration. And that will remind you that force and acceleration are directly proportional to each other, and that acceleration and mass are inversely proportional to each other. The third law talks about the fact that forces are not single, they always come in pairs. And you remember we had the little song for the third law. If you really believe that song and you remember it, and how could you forget it, then you shouldn't miss questions about the third law. So that third law song says that if the A exerts a force on the B, then the B exerts a force on the A, and you just substitute A and B with whatever the two objects are that are interacting. But the important point is that forces come in pairs, and if one object exerts a force on the second object, then the second object exerts the same force in the opposite direction on the first object. And that's what that little song is supposed to remind you of. Then we did quite a few problems that were applications of these laws, along with the force laws for gravity and electromagnetism. And I don't know how to tell you to review those other than to practice, and I'm going to give you some practice problems in a second. And at the end of this review, I'll give you an online reference where you can get more practice problems. We talked about, in particular, what happens in fluids. We talked about buoyancy. There's always a buoyant force up on an object immersed in a fluid, and that buoyant force is equal to the weight of the material that the buoyant object displaces, or that any object displaces. And in fact, there's even a buoyant force for objects in our atmosphere, because things that in our atmosphere are displacing a certain mass of air, and there's a buoyant force up that is equal to the weight of that air. And if you don't take it into account when you're making very careful chemical measurements, you'll get wrong answers. We talked about the dynamics of floating in a fluid, and I think I'll have some examples of that later on. Then we talked about special relativity, which is what happens when you have motion at very high speeds approaching the speed of light. And we saw that there were three consequences of special relativity. This is mainly what you need to know about relativity. The three consequences are time dilation, that is, time slows down for objects that are moving at high speeds, speeds comparable to the speed of light. Length contraction, that is, the objects shrink in the direction of motion when they're moving at high speed. And mass increase, objects that are moving at very high speeds have their mass increase, and the increase is described by Einstein's famous equation E equals mc squared, where E is the energy, m is the mass, and c is the speed of light. And then finally, the last topic of Unit 1 was energy, and we noticed that there are several different types. We can talk about mechanical energy, which is energy that has to do with macroscopic objects, versus internal energy, which is the energy of the atoms and molecules moving within macroscopic objects, or microscopic energy. We also noticed that you could classify energy as either kinetic energy, which is energy of motion, 1/2 the mass times the velocity squared, or potential energy, which is energy of position. So two objects that attract each other have greater potential energy when they're further apart than when they're close together. And of course, that attraction is related to one of those fundamental forces, gravity, electromagnetism, strong nuclear force, or weak nuclear force. We saw that energy is always conserved. The total energy doesn't change. And we saw that energy could be transformed from one form to another, and that happens a lot. You can go from kinetic to potential and back and forth, but the total amount of energy never changes. It's conserved, and that's the first law of thermodynamics, which we covered there. All right, I think I'm ready to start moving through the material. Excuse me. We'll skip the music. A couple of side topics, and this relates more to PS 100 in Provo, because in Provo we do talk about some supplemental topics, but I think this is worth my Salt Lake students hearing about just briefly. You might think that this relativity stuff is all really esoteric and doesn't have anything to do with us in the real world, but it does. Your GPS would not work unless you took relativity properly into account. Now, the way GPS works is described a bit on this slide. This little equation, distance equals velocity times time, is sort of the key to the way GPS works in general. So what you want to do with a GPS is measure your distance to the GPS satellite. Well, the velocity, the speed of light, which is how fast those radio signals between you and the GPS satellite travel, is well known. And you can measure the time. You subtract the time that the signal was received from the time that it was transmitted, and that gives you the time. That enables you to determine the distance. We know the positions of the GPS satellites in their orbits very well. So getting the time right and getting the position right depends on having really accurate knowledge of what time it is on the satellite. So as you can see, if you have one satellite and you measure your distance to that satellite, that means you know that you are somewhere on the surface of a sphere that is at that distance from the satellite. And if you can detect two satellites at the same time, well, you know the distance to the first satellite and the distance to the second satellite, and that means you have to be somewhere on the circle that's the intersection of those two spheres. But you need to know your position more accurately than that. And so if you measure the distance to a third satellite by timing that, well, the three spheres intersect at 2 points. So now you know you're at one of those 2 points. And to finally get your position exactly, you need a fourth satellite. That puts you on the intersection of the 4 spheres that describe your distance to the 4 satellites, and there's only 1 point possible. Now, what relativity tells us is that time is affected by 2 things. As we saw in class, it's affected by your speed. And so if you have a speed that's high compared to the speed of light, or close to the speed of light, then time will slow down. The GPS satellites are moving pretty fast in orbit, but not fast enough for that effect to be super large. It's noticeable, but not huge. The second way that time is affected relativistically is by your position in a gravitational field. If you saw the movie Interstellar, it plays on this quite a lot. So if you're deep in a gravitational field, then time slows down for you. And if you're higher up, further, not as deep in the gravitational field, then time moves faster. And that's what has a huge effect on the GPS satellites, because they're in orbits high above the Earth. They're not as deep in the Earth's gravitational field as we are here on the surface. And so time on the GPS satellite slows down. And you have to adjust for that, or you get all wrong answers about your distances to those satellites. And your GPS would literally be miles off, not just a few feet. And so there really is some practicality to the GPS, or to relativity, in terms of something that many of us use all the time. Don't know how we ever got by before we had GPS. I guess I should know, because I remember those days. GPS is great. Let's see, we talked about a little bit about Curie temperature. I'm going to pause this and rewind it. So this is material I didn't have time really to cover in class. And this talks about what happens to a magnetic field when the temperatures get high. So it has to do with electromagnetism, which I haven't really discussed much in this review. But remember, we covered two forces in detail of the four. The four fundamental forces are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. And remember that gravity and electromagnetism have very similar force laws. They both involve a constant, then the product of two quantities. For gravity, it's the two masses of the two interacting objects. For electromagnetism, it's the charges of the two interacting objects. And then all of that divided by the distance between the two objects squared. Well, Curie temperature has to do with the electromagnetic force. We saw in class that there's a relationship between the electromagnetic force and charges and motion of charges, and there's a relationship between electricity and magnetism. If you have a moving charge, that creates a magnetic field. But really the reason I want to talk about Curie temperature is to set up something that will happen way at the end of the course in Unit 4, which is explaining the magnetism of the Earth. The idea here in this movie, which I'll turn on in just a second, is that at temperatures, as temperatures increase, you get to a point where permanent magnets don't exist anymore. And so what this is really trying to demonstrate is that it's not possible to have a huge permanent magnet down in the center of the Earth. We don't have a big chunk of metallic iron that is magnetic down in the center of the Earth because the temperatures are too high. And maybe that's enough explanation. Let me just turn on the movie. So here we go.
We'll use this Canadian nickel to demonstrate the effect of heating on magnetic materials. When the nickel is at room temperature, it is strongly attracted to a magnet. If we heat the nickel above its critical temperature, known as the Curie temperature, it loses its magnetic properties. When the nickel cools, it again becomes magnetic.
Okay, so that's that. Very simple. All right, here's a question. What I'd like you to do is read and answer the question yourself. I'll pause a little bit, and then I will answer it. So take a second, maybe pause your video, answer this question, and then we'll answer it. Okay, question says, when an elevator is moving upward at a constant speed, which of these are true? Okay, the key thing in this question is constant speed. Of course, elevators don't change directions, at least not the normal ones, unless you're watching Willy Wonka, where they go all kinds of funny directions. Elevators normally go in a constant direction And if it's moving upward at constant speed, what does that tell you about what kind of motion we're experiencing? Well, if it's going at constant speed and constant direction, the motion is uniform. And from that we can immediately conclude that the net force on the elevator and on the passenger has to be zero. Why? Well, because there's no acceleration. So we'll examine the answers. A says the forces on a passenger are unbalanced, causing acceleration upward. That's not true. You're not accelerating upward because your speed and your direction are constant. B says the forces on a passenger are balanced. That's true because you are experiencing uniform motion, so the net force has to be zero. That's the same thing as saying the forces are balanced. So I think B is going to be the right answer. C says the forces on a passenger are at their maximum. No, we don't know anything about what the forces are, but we accept that the net force is zero. D says there are no forces on a passenger, so there is no acceleration. Well, no, there are forces operating on the passenger. There's a gravitational force down operating on the passenger, and there's the force of the floor of the elevator pushing up, and those two forces are in balance so that the net force is zero. So you can't say there's no force. E says the motion is not uniform. Well, yes, it is. We know what uniform motion is. It's motion at constant speed and constant direction. And so the right answer to this question is B. Here's another one. When a book and a sheet of paper with the same dimensions, that is length and width, are dropped separately from the same height, which is true? We actually did this demonstration in class. Go ahead and answer this. Okay, I hope you've had a chance to answer it. Let's analyze each of the answers and decide which is correct. A says, a few moments after they're dropped, the friction on the paper is greater than the friction on the book. That's not correct. The friction is proportional to the speed that the objects, the book and the paper, are moving through the air. So the one that's moving faster will experience the greater friction. And a few moments after they're dropped, which one's moving faster? The book. So the book experiences greater friction than the paper. B says, at the instant they're dropped, the gravitational forces on the book and on the paper are the same. That's not true either, because remember, gravitational force is directly proportional to the mass. And if we have a book and a sheet of paper, the book has greater mass than the paper. So the gravitational force on the book has to be greater than the gravitational force on the paper. C says the net force on the book is the same as the net force on the paper. Well, that can't be true either, because if the net force on the book and the net force on the paper were the same, well, let's see. That's more complicated. If that's true, you'd expect the book to accelerate down more slowly than the paper, right? Because the net forces, if the net forces were the same, the book has a greater mass, and the acceleration is equal to the force divided by the mass. So if the book has greater mass and the net force was the same, the book should accelerate less than the paper. And that's not what you see. You see the book accelerating down much faster than the paper accelerates down. So C can't be correct. D. For the paper, the frictional force is comparable to the gravitational force, so the net force is relatively small. And of course we've eliminated A, B, and C, so D must be the correct answer. But let's think about why it is. D is correct. The frictional force is comparable to the gravitational force. So think about the paper as it falls. Oh, here's a piece of paper. As the paper is falling, there's a gravitational force down on it. And what forces are there in addition to that? Well, there's a frictional force up. And because the frictional force up is almost as great as the gravitational force down, the net force on the paper is relatively small, and so the paper doesn't fall very fast. It doesn't accelerate quickly as it drops. On the other hand, if we're dropping the book, the gravitational force down on the book is large, and the frictional force up on the book is much less than that, so there's a large net force down, and that's why the book falls more quickly. And I hope I haven't spoiled the next question by saying that. Let's move on to the next question. When a book and a sheet of paper with the same dimensions, length and width, are dropped with the paper on top of the book, which is true. We did this demonstration in class too. So think about this, read the answers, answer it, and then we'll discuss them. All right, let's analyze each answer. A says the net force on the book is less than the net force on the paper. Can that be true? No. The book and the paper accelerate down at the same rate. The mass of the book is greater than the mass of the paper, and so the force on the book has to be greater than the force on the paper, or they would not accelerate down at the same rate. So A cannot be correct. B says the book and paper accelerate at about the same rate. So far so good. That's what we observe. When you put the paper on top of the book, they fall together. Because the net force is determined mostly by the gravitational interaction with the Earth. For both book and paper, friction is small in comparison. Now that sounds promising. I know they accelerate down at about the same rate, and the net force is determined mostly by the gravitational interaction with the Earth. The difference when you put the paper on top of the book is that the book experiences friction from the air, and because the book is in the way, the paper doesn't experience the friction from the air. So you've taken away most of the frictional force on the paper, and now it's just gravity mostly operating on both of them. There is friction operating on the book, but the frictional force on the book is a lot less than the gravitational force on the book. And so B looks really promising. That looks true. C says the net force on the book is the same as the net force on the paper. Well, C can't be true. Why? Well, again, it's Newton's second law. If the net force on the book and the net force on the paper were the same, then you would certainly expect the paper to accelerate faster than the book. But it doesn't. They accelerate at the same rate. Why would you expect the paper to accelerate faster? Because its mass is less. And remember, the amount of acceleration you get is inversely proportional to the mass. I think if you understand these two questions, you'll be able to answer pretty much anything we can ask of related questions about gravity and acceleration and force. So these are good ones to make sure you've got clear in your head. Here's one about buoyancy. Seawater is more dense than fresh water. If the same iceberg is shown in each picture, which body of water is fresh? Take some time and think about this and answer it. Alright, so we've got two pictures, and if you look at picture A and picture B, you see the difference is that the iceberg is floating higher in picture B than it's floating in picture A. And so why would it float higher in one than the other? Well, it certainly has something to do with the density of the fluid. Remember that the buoyant force up is proportional to the mass of the fluid that is displaced, or really the weight. I should use the word weight. It's equal to the weight of the fluid that's displaced. In picture A, the iceberg is deeper in the water. It's displacing more water. In picture B, it's displacing less water. The iceberg weighs the same in both cases, and so the difference is the buoyant force. The buoyant force in A is greater than the buoyant force in B. No, that can't be right, can it? Since they're both floating and they're both not accelerating, the buoyant force is equal to the weight in both cases, A and B. And so why does B float higher than A? Well, salt water is more dense than fresh water. That means you don't have to displace as much salt water to get a certain amount of buoyancy as you have to displace fresh water. So which body of water is fresh? A has to be the fresh water. B has to be the salt water. Of course, if you've gone out and floated in the Great Salt Lake, I've lived here for a long time and I've never actually done this, but I'm told that if you go float in the Great Salt Lake, you will float higher in the water than you float in fresh water. And of course that makes perfect sense because that salt water is very dense. You don't have to displace as much of it to have that amount be equal to your weight as you do if the water is fresh. So you can tell from the given information. So A is the correct answer. Let's see. We talked about convection in fluids. I think we can go through this pretty quickly. When you heat a fluid up, the fluid's density decreases, and therefore it is buoyed up by the other fluid around it, so less dense fluid rises. And cool fluid is more dense than warm fluid, so if you have cool fluid, it will sink. And of course, if this is happening in the atmosphere, say during the daytime over the land gets heated up by the sunlight, and air gets heated up over that land. Since it's warmer air, it rises out over the ocean. As it flows out there, it sinks back down, and you get a circulating pattern, which is opposite to the direction that these arrows show here. This figure is kind of messed up. At night, the reverse happens because the land cools off more quickly than the ocean. The bottom line here is water is hard to change its temperature very quickly relative to land, where it goes up and down real quickly. So at night, what happens is you have cool air out over the ocean, and you have cooler air over the land because the land cools off quickly. And so over the land, the air sinks, flows out over the ocean warms it up, and it rises. So the arrows are in the correct direction for nighttime. They're in the wrong direction for daytime. But this collective motion of the fluids causes circulation, and that's why you get sea breezes that reverse direction at the seashore. And there are lots of other examples where you get convection in fluids. Later on in the course, we're going to see that this happens within the Earth's mantle. So you get molten rock rising because it's hot and less dense, and you get cold, solid rock sinking because it's colder and more dense, and that creates circulation patterns even within the Earth itself. When you have a pot on the stove, you see this happening because the heat is being put in at the bottom of the pot, and that fluid is less dense, so it rises to the surface where it cools off and then sinks back down, and you'll see it circulating. That's probably enough to say about convection. Here's another good question. Applications of the laws of force and motion. Aboard the International Space Station, it is observed that there is no convection in fluids. Why is that? Let's put together ideas about gravity and convection. Let me pause and let you answer. All right, let's analyze each of the answers and decide which one's right. A says because the laws of physics are different there than on Earth's surface. Well, that statement is a violation of one of our fundamental assumptions from day one. That is the assumption that the laws of physics are the same everywhere. What do we call that? I got to think here. What do we call that? It's position symmetry, right? That violates position symmetry, so A can't be correct. B says because pressure does not increase with depth in a free-falling fluid. That's actually a true statement and the right answer. Let's think about why that's true. Well, if you have a falling fluid, then you don't have the fluid above pushing down on the fluid below because all the fluid is accelerating in the same way at the same time. And so pressure doesn't increase with depth in a free-falling fluid. C says because the orbital motion of the ISS is so fast relative to the speed of convection. It's a true statement, but it has nothing to do with why there be no convection in fluids. D says because the ISS is a closed container, and it is a closed container, but again, that has nothing to do with why there's no convection in fluids in the ISS. It's because everything in the ISS is in free fall. It is accelerating down towards the center of the Earth. That's what so-called zero-G is. The gravity is still there. It's just that everything is falling. Why doesn't it fall down and hit the Earth? Well, because there's a motion perpendicular to that direction also, a uniform motion, and so as the ISS travels, it's falling, but it never hits the edge of the Earth. Okay, so B is the correct answer. Thinking about motion in orbit, think about a flying space shuttle. What are the forces operating on it? Are there any forces? Well, sure. What kind of motion is the space shuttle undergoing when it's in orbit? It must be accelerated motion because it's not moving in a straight line, it's moving in a circle. Since the direction is always changing when you're flying in a circle, the motion must be accelerated, which means there must be a net force. What is the net force? It's the force of gravity causing it to fall towards the Earth. Do you have to fire the engines to stay on orbit? The answer to that is no. Why not? Well, because the shuttle has a sideways component to its motion in addition to the falling, and if you add those two together, it's always falling, but falling in a circle around the Earth, and the Earth curves away. If you remember the Newton's cannon demonstration or video that we looked at in class, I think that makes it all pretty clear. Let's consider one more problem, the broken elevator. So let's say you're on an elevator and the elevator cable breaks. What are the forces on the passenger right after the cable breaks? Are there any? Well, what kind of motion is the passenger undergoing after the cable breaks? The passenger will be accelerating downward. That means that there is a net force on the passenger. And what is the net force on the passenger? Well, it's the gravitational force down, and that's the only significant force, and so the passenger accelerates downward. The elevator also accelerates downward at the same speed because it also experiences a gravitational force down. The gravitational force is proportional to the mass of the passenger and the mass of the elevator, and that works out in such a way that it exactly cancels, and so they both experience the same acceleration even though the forces on them are different. What about when a shuttle or another spacecraft launches? What are the forces on the astronaut? Well, again, the best way to think about that is to think in terms of the motion to start with, and then you can figure out the forces. Or if you want, you can start with the forces and figure out the motion. So if I were an astronaut sitting in one of the seats on the shuttle as it's launching, what forces do I experience? Well, there's the gravitational force down because I am attracted downward towards the Earth. But that's not the only force. There's also the force of the thrust of the rockets, which is upward, which is of course transmitted through the body of the shuttle to the back of my seat. So that is accelerating and pushing me upward. Which force is greater? Well, the thrust upward must be greater than the gravitational force downward because the direction that I'm accelerating, the direction I'm speeding up, is in the upward direction. So the shuttle starts at rest and then it accelerates upward until finally it reaches orbital velocity, something like 17,000 miles per hour. Okay, do you remember the experiment we did in class with the spinning chair and the weights? We pulled the weights in and the chair sped up. Why does the chair speed up when the weights are pulled in? Take a second and answer this one. Why does the chair speed up? Let's analyze each of the answers. A says conservation of energy requires the speed to increase. Is that what's being conserved in this experiment? Energy is always conserved, but that's not what causes the speed to increase. It's another conservation law. B says conservation of angular momentum requires the speed to increase. Do you remember the definition of angular momentum? Angular momentum is the mass times the rotational speed times the distance from the center of the rotation. And if we're conserving angular momentum and we pull the weights in, well, the mass is staying the same and the distance from the mass to the center of the rotation is decreasing. If that's decreasing, and if the mass is staying the same, then the rotational speed has to increase to make up for the decrease in distance. So it is conservation of angular momentum that requires the speed to increase. It's not linear momentum. That has to do with motion in straight lines, and it's not the French judge. So B is the correct answer. One last little video. I think this is the last one. This is just something sort of fun that we didn't cover in class. It has to do with one of the paradoxes that comes about because of relativity. So watch this one just for a little bit of entertainment. Here we go.
No matter how long they've been around, no matter whether they tick-tock, chime, or say cuckoo, all clocks obey the rules of relativity. Naturally, these rules apply to the human clock. With a time-keeping device called metabolism, it starts running even before the moment of birth. And in a relatively predictable fashion, it keeps running to the end. But what would happen if the human clock were moving at nearly the speed of light? To find out, consider these identical twins, Albert and Henry. From the very outset, their biological clocks start out in perfect synchronization. Soon enough, however, the best laid plans of mother and father alike get out of sync. Instead of an orthodontist, Albert becomes a scientist. Henry chooses what's left of the wide open spaces, open space itself. Especially for identical twins, the first parting is such sweet sorrow. Nonetheless, traveling at nearly the speed of light, Henry has no trouble leaving Albert behind. This is Henry's first long haul for his new boss, the Interstellar Baiting Company. Destination, Zog, 10 light years away. Assignment, take a load of ordinary white bread and exchange it for Zoggy cakes, those delicious little buns that all the earthlings crave. But that's not what's so extraordinary. If Henry could compare his clock to Albert's clock, he would find Albert's clock running slow. And if Albert could compare his clock to Henry's, he would find Henry's clock running slow. And that spells paradox. How can each one be slower than the other? Fortunately, in the theory of relativity, there's no problem at all. For one thing, there won't really be a problem as long as the two of them are far apart. But what will happen when they're not far apart? Say, when they get back together for a family reunion. Again, in the theory of relativity, that's no problem. Brother Henry, at nearly the speed of light, will take about 10 years to reach Zog, 10 light years away. And then another decade to haul his buns back to Earth. To Albert, that's around 20 years. But to Henry, the twin who's actually en route, the situation seems different. Since it's Lorentz contracted, the distance to Zog seems like a milk run. A few hands of solitaire, 40 winks, and as far as Henry's concerned, it's hello to the bright lights of Zog City. Then, equally quick, because the distance is again Lorentz contracted, it's back to Earth just as fast. And so, when they do get to compare those biological clocks, while the result is amazing, there's no paradox at all. Henry, the twin who zoomed away and then came back, has only aged a couple of months. But Albert, the twin who never switched inertial frames, has aged 20 years. And so, even among relatives, time is relative.
Okay, so that was just for fun. Let's do a few more problems. This is the problem of the fly hitting the train. And you remember from the third law that when the fly collides with the fly exerts a force on the train. If the fly exerts a force on the train, then the train exerts a force on the fly. Sorry. The forces are equal and opposite, so they experience the same force, but the acceleration they experience is definitely not the same. The fly has far less mass than the train does, so the fly accelerates 10 to the 10th power times more than the train does. The train hardly accelerates at all. However, if you have a lot of flies, like, 10 to the 10th flies, which is really, really a lot, that'd be 10 billion flies, then the train would be experiencing quite a lot of force. And air friction can be explained if you think of the air molecules as being like the flies. So you have lots and lots, even more than 10 to the 10th times of air molecule collisions. And so that's what actually causes friction. All right. Question for you then. When the fly collides with the train, pick the best answer. All right, let's analyze the answers. A says the force of train on fly is greater than the force of fly on train. Well, A is a violation of the third law. The third law says that if the fly exerts a force on the train, then the train exerts a force on the fly, and those forces are equal and opposite. So the force of train on fly is not greater than the force of fly on train. It should be the same. B, likewise, is false. It says the force of train on fly is less than the force of fly on train. C says the force of train on fly is the same as the force of fly on train. And that is a true statement. That's obeying the third law. D says linear momentum is not conserved. Well, that's false. Linear momentum is conserved in collisions. E says angular momentum is not conserved. That's false, because angular momentum is also always conserved. Next. C is the correct answer. Let's think for a second about air friction. Say that a plane drops a package. We'll use a package rather than a bomb. My question is, which picture assumes that there's no air friction, and how can you tell? Well, in the top picture, the package is dropped from the plane flies along, the package falls, and the package falls directly underneath where the plane is. In the second picture, the package lags behind the plane, so the plane falls over the target spot before the package gets there, and the package is going to fall short. I think we can answer this question if we analyze what the forces are on the falling package with and without friction. In the top frame, as the package falls, what forces are on the package? Well, there's only one. It's the gravitational force down that is accelerating the package downward. The package has some motion in the direction of the plane, and so it's moving it in that direction, and there's no force in that direction, and so the package and the plane maintain the same speed in that direction from left to right across the screen. In picture B, what are the forces on the package? Well, now there's air friction. So there's a gravitational force down once the package is released, and there's also friction, which is opposing its motion. So it's got a motion from left to right across the screen, and friction is opposing that, so there's a frictional force backward. There's also a frictional force up that slows the package's falling. It's opposed to the gravitational force down. So that's why the package lags behind the plane, because it's experiencing friction. The plane, of course, has forces on it too. Gravity down, lift of the wings up, those are balanced, so the plane flies level. And then there is a force from the propeller pushing backward that causes the plane to accelerate. I'm sorry, I got that wrong. There's the force of the air on the propeller causing the plane to move forward. There's also frictional force backward, and presumably those two are balanced too, so that the plane flies forward in a straight line, non-accelerated motion, whereas the package is experiencing accelerated motion. So it says describe the motion of the package. In both cases we've done that. There's no air friction in the top frame, there's air friction in the bottom frame. I can summarize pretty much everything you need to know about relativity on this slide. Relativity depends on two postulates or assumptions. They are the special principle of relativity, which says that all non-accelerating frames of reference are equivalent. They're all equally valid. That's the idea that if you were in a spacecraft that had no doors or windows, you couldn't see out, there's no way that you could tell whether or not the spacecraft was moving as long as it's not accelerating. That's that idea. The second postulate of relativity is that the speed of light is constant no matter what frame of reference you're in, and it follows from that nothing can travel faster than the speed of light. But if you apply these two postulates to motion, the consequences are given down below here. There are 3 or 4 that are important. One is time dilation, that is, time for a moving object slows down. The second is length contraction, that is, a moving object moving near the speed of light gets smaller in its direction of motion. The third one, which I didn't mention earlier, is that simultaneity is relative to an observer, so events that are observed to be simultaneous by one observer may not be observed to be simultaneous by a different observer who's moving at high speed relative to that. Then the fourth consequence is mass increase. That is, as objects move faster and faster closer to the speed of light, their mass goes up. That probably deserves a little more discussion. So let's talk about relativistic mass increase. If you accelerate particles in a big particle accelerator like the Large Hadron Collider, which recently restarted over in Europe, you can get those particles up to very high velocities, speeds very close to the speed of light, like 99.99% of the speed of light. That accelerator exerts a constant electromagnetic force on those charged particles. And we know that force equals mass times acceleration. The problem is, as the speed gets close to the speed of light, the acceleration can't continue to increase. And yet there's still a force there. And so if A can't get bigger, the only thing that can change is mass, and mass does get bigger. And so what's really happening is we're exerting a force by using energy on that charged particle, and that energy is actually converted into mass. So the energy shows up as mass in the particle, and that leads to Einstein's famous equation, E equals mc squared. So the mass increases when you get to high speed. The mass increase is happening because of energy, really, not because of speed. Because remember, kinetic energy is 1/2 the mass times the velocity squared. Well, the velocity can't go up when you get close to the speed of light, but the mass can. So what's really conserved is not mass by itself, it's the sum of mass and energy together. It's mass energy. So mass can turn into energy, and the equation that describes the conversion is E equals mc squared. Got that? That's about all you need to know about that. We talked about light clocks when we were talking about relativity. That is a clock that is, it's a thought clock really, it's not a real one, where you have a pulse of light bouncing back and forth between a pair of mirrors. And let's say the mirrors are 4 meters apart. Each time the light is reflected off a mirror is a tick of the clock. And that's the way it behaves when it's stationary. But if you start the clock moving at a high speed, say at 3/4 of the speed of light, If I'm watching that from a position on the ground as it goes by, what I see is the light leaves one mirror and it travels up towards the other mirror, but because the clock is moving left to right across the screen at 3/4 of the speed of light, I don't see it travel a straight line up and down. Instead, it takes this diagonal path. And so while it's traveling up 4 meters, it travels sideways 3 meters. Sorry, the figure is not to scale. And you can solve the distance that the pulse of light has to actually travel along that diagonal using the Pythagorean theorem. This is the hypotenuse, so the square of the hypotenuse is equal to the square of the sum of the sides. So let's see, that would be 4 squared is 16, and 3 squared is 9. 9 plus 16 is 25. The square root of 25 is 5. So the light has to go 5 meters. But it's going at the speed of light, which is constant. And since it has to travel 5 meters when it's moving sideways, instead of the 4 meters it travels if it's stationary, then that clock has to run slow. Measured light clocks are measured to be running slow, and it's not just light clocks, it's every kind of clock that does this. So that's the origin of time dilation, which I think is probably the easiest of the relativistic effects to understand. And I think I do have one last movie here about light clocks, which we saw in class, but I'll play for you again. Here it goes.
An observer could not determine whether he was in motion by measuring the speed of light, since that speed is the same for all observers. And that meant age-old notions about time and space had to change. And though Poincaré himself shied away from examining the consequences, Lorentz developed the equations needed to show precisely how much rulers would have to contract and clocks would have to slow down when they were in motion. The essence of his reasoning can be seen with the aid of the simplest possible clock. 2 mirrors a fixed distance apart, with a light beam bouncing back and forth between them. Each bounce of the beam is a tick or a tock of the timepiece. To Henry, his clock is stationary and altogether ordinary. But for Albert, that clock is moving. And between tick and tock, he sees the light beam trace a diagonal path, which means it's traveling a longer distance. But the speed of light is the same for all observers, so the light must take a longer time to travel the longer distance. Therefore, Albert believes the moving clock runs slow. But how slow?
Just as a reminder, if you want more practice problems, a great place to go is ps100.byu.edu. Look on the left-hand side of the screen under Help Resources, click on Practice Problems, and that will give you more problems to go with each chapter, along with some tutorial material. This is a really good way to review the material, either for the Unit 1 exam or for the final exam for the course. Good luck to you, and we'll see you in class.